Hi, physics. Mr. Janowski here. We're about to start the next chapter. So the last chapter we did was chapter 10, and that's rotational motion. And we dealt with things like spinning bicycle wheels and socks going around in the dryer and in the washing machine and things like that. So what we're about to start here is going to be a little different in scale compared to those things. It's actually going to be a lot different in scale. It's going to basically be the biggest things that there are. So let's get started with that. I like this stuff a lot. This chapter will deal with big question kinds of things. So I'm looking forward to it. Hopefully you're going to enjoy it. So let's get started. So let's start here. Seems like a good place to start. The start of everything. So what is the Big Bang Theory? And I'm not talking about the sitcom. I hate that sitcom, actually. I hate it tremendously. Me and my brother hate it. I get angry just thinking about it. I'm getting angry right now. So me and my brother both hate it. Both my parents and my sister love it for some reason, but I personally hate it. But I'm not talking about the sitcom. I'm talking about the actual theory. So you've heard of this theory before. So take a second, think, what is this theory? So if we were in class in person, I would have you turn to your neighbor right now and discuss it. We don't have that luxury at this point. So let's just see. So the Big Bang Theory is the theory that approximately 13.8 billion years ago, so there's 13.8 billion if you write it out, the universe began expanding from a very dense, very hot state. It may in fact have been infinitely dense and infinitely hot, but we're not sure because the physics we have doesn't work before 10 to the minus 43 seconds after the Big Bang. So there's going to be some scientific notation in this chapter. So hopefully you're comfortable with that stuff. But yeah, 10 to the minus 43. Sometimes we write numbers this way because it would really be a pain to write them out this way. So this is what 1 times 10 to the minus 43 looks like. So this is a incredibly small number. So because here's your decimal point, and then you go 43 places to the right. Yeah. So that's the Big Bang Theory. So in history class, you often deal with timelines of different events and different eras in history. So you might deal with like the 7 Years' War leading to the Stamp Act, leading to the Boston Massacre, I don't know which one came first, and the American Revolution. And then you'll see the whole timeline, and it'll show you the different dates of these things and the dates of different battles and when people were in office and different things like that. And yeah, when you learn that kind of thing in history, it's frankly adorable. Because what we're looking at here, this is a timeline, but on this timeline, this is literally everything that has ever happened. This is a timeline that starts at the beginning, since the Big Bang, and then goes up to the present tense. So this timeline is running vertically, so the beginning is down here. And you'll notice the scale of this timeline as we go up, it's not very even. This is kind of super logarithmic. So from here at the bottom, Planck era up to right up here, right above the particle era, right before the era of nucleosynthesis, that whole amount of time is from time zero, the very beginning of the Big Bang, up until 1/1000th of a second. And then, the next amount of time up, the next space up, gets you to 500,000 years after the Big Bang. And then the next amount of space up gets you the rest of the way, the other 13.8 almost billion years. So I'm not going to go through all this in great depth. Let's hit a couple of the highlights. So down here at the very beginning, this would be time zero. And from here to here, we have what's called the Planck era. And you'll notice what's going on in the Planck era. We have question marks because our physics doesn't work back here. Basically, we have our two best theories of big things and small things, which are the general theory of relativity is the theory of the big thing, and the quantum mechanics and the standard model, all of that is our theory of the small things. And when you try to bring them together, which you have to do before this time, you start getting nonsensical answers, which is kind of a shame. So yeah, from zero up until this tiny fraction of a second after zero, after the Big Bang, we don't really know what's going on. kind of a mystery. We call it the Planck era, named after Max Planck, one of the founders of quantum mechanics. After that, you get to the gut era. That's grand unified theory. More on that to come. And then different things start happening. Let's see. We start to have elementary particles. And we have lots of antimatter at this point, up in the first 1,000th of a second. But then after that, we get to the era of nucleosynthesis. So we're starting to form the nuclei of atoms. So we've got protons and neutrons. The protons and neutrons have formed a couple of atomic nuclei. The electrons are there, but they're not joined with the protons and neutrons yet. And by this point, 1,000th of a second after the Big Bang, antimatter has become rare. So you have that for a while. And then this bar here, 500,000 years. It should really say 380,000 years, but it says 500,000 years. We know the time pretty well. It's actually 380,000 years. At this point, that begins the beginning of atoms. So up until this point, we've had nuclei. We've had protons and neutrons together doing things. Basically only hydrogen and helium and a little bit of lithium. But we only had the nuclei, and everything was still too hot, and the electrons couldn't hold on to those nuclei for very long. So for the first 380,000 years, that's what you had. And then after that point, things have spread out far enough, they've cooled down enough, and now the electrons can join with the nuclei. This is also called recombination, is another name for this, but an important time. At this point, basically, the universe becomes transparent, and you can see. Light is able to travel throughout the universe at this point. More on this to come. So after that, we have the era of atoms. So we're starting to get stars forming, and you have just stars forming for about 1 billion years, and then eventually gravity starts to pull the stars together into galaxies. We're still not exactly sure how the galaxies formed. We've got different ideas on this, but we're not exactly sure. And then that gets us up to, the next 12.8 billion years after this, gets us up to the present. So in this thin blue line across here, this is the present. This is, all of recorded history is in this thin blue line right here. This is me being born, and then years later, you guys being born, up until everything that's going on right now. So all of the history you would learn in history class is all contained in this thin little blue line, this tiniest little sliver of this timeline. So yeah, this is one of the things I really love about physics, is we get to deal with timelines where we're looking at literally everything that has ever happened. We do the big things. That which is not physics is stamp collecting. So I've just said a lot of fairly extraordinary things, and Carl Sagan had this idea. This is sometimes called Sagan's razor. This famous quote of his, that extraordinary claims require extraordinary evidence. So I've just told you some fairly extraordinary things, and I have to give you evidence for them, because if I don't give you evidence, then I'm not doing science. So yeah, Carl Sagan. If you're not familiar with him, he did very famous popularizer of science. He did the original Cosmos series back in 1980. Then, yeah, he had a funny way. I have a Carl Sagan t-shirt. He had a funny way of talking. He'd often say like billions and billions of stars. That's my best Carl Sagan. But he was, great popularizer of science. Didn't live all that long, unfortunately, which is a shame. So anyhow, back to the evidence for the Big Bang Theory, because I have to give you evidence for things. So that we're going to deal with two pieces of evidence. And of the two pieces of evidence, the first piece is going to be kind of the easier one to understand. And this is the idea that the universe is expanding. So maybe you've heard that, but we didn't always know that. So I'm giving credit right here to Edwin Hubble. This is the Hubble telescope guy. He had nothing to do with actually making the telescope, but the telescope was named in his honor. So Hubble didn't actually come up with this idea that the universe is expanding. There's an old kind of saying in science that whenever someone makes a big discovery, there's a few stages it goes through. And in the first stage, people say, that's not true. In the second stage, they say it's not important. And then in the final stage, they give credit to the wrong person. So Hubble is kind of the wrong person. He's not completely the wrong person. The first person to come up with this idea, and the idea for the Big Bang, kind of in total, although he didn't call it the Big Bang, he called it the primeval atom, is actually a Belgian priest / scientist named Georges Lemaitre. Lemaitre was working around the same time as Einstein. He took Einstein's ideas about general relativity, which we'll talk about in this chapter, and he realized that Einstein's ideas could be interpreted as suggesting that the universe was expanding. So Lemaitre was all excited about this, and he went to Einstein and he told Einstein about this idea. And Einstein said something, the quote is something like, "Your mathematics are correct, or your calculations are correct, but your physics are abominable." Because he's saying, well, you did the math correctly, but the idea you've come up with makes no sense. He's saying this to Georges Lemaitre. Because Lemaitre's idea is that the universe is not eternal and all kind of locked in place. It's actually expanding. And Einstein, brilliant as he was, wasn't ready for that idea. No one was. Everyone kind of thought the universe was just kind of eternal and locked in place. And to Einstein's credit, he did the right thing. Years later, just a few years later, actually, when it was clear after Hubble came up with his evidence that Lemaitre had the right idea, that the universe actually is expanding, Einstein said, yeah, I was wrong. He called this, the greatest blunder of his career, to say that the universe wasn't expanding, when in fact it is. So Lemaitre actually had the idea first. Hubble does deserve credit because Hubble was the guy who actually got the data and the evidence for this. Hubble took a lot of observations of distant galaxies and was able to figure out that the distant galaxies are expanding. So, meaning most galaxies, if a galaxy is very near to our own galaxy, the Milky Way, so like Andromeda, for example, is fairly close as far as galaxies go to the Milky Way. If you're very close to the Milky Way, you might be coming towards the Milky Way, and Andromeda actually is. And Andromeda is heading right towards the Milky Way, and eventually it will collide with the Milky Way. But if you go to the more distant galaxies, they're going to be moving away from our own galaxy, away from the Milky Way. And the further away you go from our galaxy, the faster they're moving away. So that's this idea, which is called Hubble's law. So in Hubble's law, the velocity at which the galaxy recedes from Earth, meaning the velocity at which it goes away, is equal to h naught. This is just called Hubble's constant, which the different ways of measuring this, times the distance. So basically, if D is a small number, then it will be moving away from Earth kind of slowly. If D is a big number, it will be moving away very quickly. So I feel like this video is going to get to be long because I'm going kind of in depth with this stuff, but whatever. It's worth it. This stuff is important. So yeah, in a nutshell, most galaxies are moving away from us. And if the further away the galaxies are from us, the faster they are moving away. So yes, the universe is expanding. How is this evidence for the Big Bang Theory? Well, the fact that the universe is expanding implies that at an earlier time, everything in the universe was much closer together. So if you look at this picture over here, if this top plane right here is the universe now, and everything is moving apart, if you went backwards in time, so going down in this is going backwards in time, if everything right now is moving apart, that implies that if we looked at it yesterday, everything would have been a little bit closer together. And if we looked at it the day before that, it would have been closer together. And if you look back a million years or a billion years or 10 billion years, the things would have been closer together. So what you do is you look at all the galaxies, you figure out how fast they're all moving apart, then you do the math and you figure out, well, if they're moving apart this fast now, at what point would they all have been right on top of each other? And you figure it out, you run the clock backwards, and it turns out it's about 13.8 billion years. So this is our first piece of evidence for the Big Bang. So kind of heady stuff, but of the two pieces of evidence, this is kind of the clearer and the easier one to understand. Now we get to the other one. So this is going to be story time. This is a nice history lesson. So back, I think they built this thing originally in the 50s. This is called the Holmdel horn antenna, and this is in Holmdel, New Jersey. So here, if you want to drive from 321 East 3rd Street, which is where the school is, and drive to Holmdel, New Jersey, it'll take you about an hour 44. to get all the way out to the Holmdel horn antenna. So they built this thing back in the 50s, and let me just kind of explain what's going on with this thing. So it looks kind of like a big cornucopia, basically. So maybe you can tell this. The idea is that you would point this thing out into space, and the light would come down into here, reflect off of here, and go back and kind of get funneled up to here. And in this little room, this is where you would have all the instruments that are measuring your light. So you can see the two guys sitting on the platform here. So these guys would walk up these stairs, go up into here, and they would measure this. And you can see this thing is on this big wheel that lets it twist around a certain way. And maybe you can tell from this picture, and definitely from this one, it's also on another kind of circular rotating disc. So between this circle that turns and this circle that turns, you can point this thing anywhere you want in the sky. So anyhow, they made this thing back in the 50s, and this was basically put up there to look at our first satellites and just read signals off of those things. So after a while, they didn't need it for that anymore, so they gave it to a couple of guys who we'll meet on the next slide. And, their names are Penzias and Wilson. And they let these guys start doing some radio astronomy with this. So what they did is they said, great, so first thing we've got to do is get just kind of a baseline reading of this. So they pointed this thing out into space, and they aimed it purposely out towards the middle of nothing, where they didn't expect to see anything, and they turned it on. And to their surprise, they got a very weak signal. And they thought that was strange, so they checked another area of the sky that they thought was empty, and they checked that one, and it turns out they were still getting a very weak signal. So not a very weak signal. It's also called noise. Not anything big, but they expected to get no signal at all. So the fact that they were getting anything was a little bit surprising. So they kept checking different places. They kept getting, just a tiny bit of signal. So then they realized, okay, well, we're fairly close to New York City. So maybe what's happening is radio and TV stations in New York are broadcasting, and it's bouncing off the atmosphere, and our satellite, our collector is accidentally picking that stuff up. So, they aimed it purposely at, New York City, and to their surprise, they were still getting that very weak signal. The signal wasn't getting stronger when they aimed it at New York. So they figured out, all right, well, it's not the signal, it's not coming from New York. So they took everything apart, cleaned everything, checked for bugs, checked all the wires, make sure there wasn't a short or anything. Then they put it all back together, and they turned it on, thinking that, whatever the problem was, we must have fixed it. And of course, they still got a very weak signal. So if you look at this thing, you can see this is just sitting out in the middle of a field. So different things are going to happen to something that you leave way out in the middle of a field. So yeah, obviously it gets snowed on, and it gets all kinds of weather and things like that. But another thing, kind of just like a statue in the park, is birds are going to land on this thing. And so it turns out that birds had been living in this thing, and they do what birds do, which is they crap all over everything. So they decided, we figured it out. This tiny little signal, it is bird crap in our telescope. So let's go up there, we'll scrape it all out, we'll turn it on, we'll get nothing. So they did that, they cleaned it all out, they turned it on, and they saw that weak little signal. And sadly, I'll tell you now, because I'll tell you in the video too, they chased all the birds away. The birds kept coming back. They couldn't convince the birds not to come back. So eventually they shot all the birds that were trying to live in this thing. To no avail, because it wasn't the birds' fault. It wasn't actually bird crap in this satellite that was causing this annoying signal. So after a while, one of their colleagues said, well, you guys are not so very far from Princeton, and there's some astronomers in Princeton doing radio astronomy. Why don't you talk to these guys and see if they have any idea what's going on? So the Holmdel guys, Penzias and Wilson, they called Princeton, and they talked to those guys, and right away the Princeton guys knew what was going on. And they were a little bit upset about this, because the Princeton guys knew right away that the Holmdel guys had discovered evidence for the Big Bang. What they had, this weak little signal, is actually what's called the cosmic microwave background, or CMB. And the guys in Princeton had theorized that this would be a thing, and they knew what it was. They had predictions about how strong this signal would be, and they just couldn't figure out how to actually find it. And meanwhile, the Holmdel guys, they accidentally, without even looking for it, found this signal. So this was 1964. So both groups, the Princeton group and the Holmdel group, they both wrote up papers about this. The Holmdel guys wrote up the paper about how they accidentally made the discovery, and the Princeton guys wrote up another paper about what the discovery meant and all the theory behind it, and they both got published at the same time. And then it was 14 years later, in 1978, somebody gets a Nobel Prize for this. So do you think it was the Princeton guys who had the theory and the ideas and everything? Or do you think it was the Holmdel guys who thought they had discovered bird crap? It was the bird crap guys. Yeah, the bird crap guys won the Nobel Prize for this. So this is Penzias and Wilson in front of their famous Holmdel horn antenna. So these guys discovered the CMB, the cosmic microwave background. This is the second piece of evidence for the Big Bang. So everywhere you look out into deep space, you see this background of light. So it's called a background because it doesn't matter where you point your telescope, it's always there in every direction. So you get a background of light corresponding to a temperature of 2.7 Kelvin. So what does that mean for light to have a temperature? If you're taking astronomy, you would know this is what Wien's law is. Wien's law keeps coming back at us. But basically, you know the idea that if you heat up the element on like an electric range, first of all, when it's cold, it's just black. And then as you heat it up, it starts to get warmer and it starts to get kind of reddish orange. And if you keep heating it up more and more, it'll start to get orangey yellow. And that's about as hot as your range is going to get. But if you could heat it up even more, eventually it would start to glow kind of, blue and white and things like that. So that's the idea of things that have a temperature putting out certain colors. So this background light has this temperature that is so very close to absolute zero. It's less than 3 degrees Kelvin above absolute zero, but it is something. It is not zero. So what they had discovered is this earliest light in the universe. So you had the Big Bang at time t equals zero, and then that 380,000 years later, this is what's called recombination. This is when the electrons the universe is spread out enough and cooled down enough so that the electrons can actually recombine with the nuclei, and so you start to have atoms at this point. So up until that point, the universe was so hot and dense that light couldn't travel anywhere, because the second it went even the tiniest bit of distance, it would run into something and it would be stopped. It wasn't until 380,000 years after the Big Bang that it had cooled down enough that light can actually travel. The universe becomes transparent. We'll see it on the graph again. At that point, at 380,000 years after the Big Bang, this light would have been incredibly hot. It would be way more than 2.7 Kelvin. I don't know how many, tens of thousands or maybe even hundreds of thousands of degrees Kelvin the light would have been. But in the intervening 13.8 billion years, because the universe has expanded and expanded and expanded, that light has gotten redshifted, similar to the Doppler effect. It's complicated. I don't want to go too far into that because this video is already getting really long. Hopefully you're interested, because I find this stuff fascinating. So here are a couple of videos. You should watch both of them. I'll put links to them in the description, of course, where I'm not making up the bird crap story. That is actually part of the scientific lore. These guys completely accidentally discovered evidence for the Big Bang when they thought they had discovered bird crap. So watch them both, especially in the second video. They're talking about it. And I forget which one's talking. It's either Penzias or Wilson. I forget which one is actually giving the interview. But he says, up until this point, so Hubble's ideas, those are back in like the 1930s, the idea that the universe is expanding. So that was one good piece of evidence for the Big Bang. But up until this point in 1964, it was still not a widely accepted theory. And then once they made this discovery of the cosmic microwave background, and the thing they discovered exactly matched what the Big Bang theory predicted, after this point, pretty much everyone right away jumped on board and said, oh, you know what? Yeah, it's the Big Bang. So among professional astronomers and physicists, and the people who study this part of astronomy and physics in particular are called cosmologists, not cosmetologists, cosmologists. Um, yeah, this idea that there was a Big Bang it's kind of been accepted science since 1964. There's not really any debate about this among the people who study this professionally. So uh, I'm kind of obliged to say that in science, we don't prove anything, and we always leave the door open, and there's always a tiny bit of doubt, and we're always willing to go back and re-examine our ideas if, in the light of new evidence. But having said that, again, no one who does this stuff professionally has had any real doubt about the Big Bang since 1964. This was kind of the nail in the coffin for the other ideas. The main other idea was called the steady state universe. But yeah, the Big Bang. So here is a baby picture of me. So this is me. I don't know if this is exactly the day I was born or a day or two after. I feel like maybe they cleaned me up a little bit and put me in the jammies. So notice, the little red, white, and blue stars in the background. That's because I'm a bicentennial baby. So that's me on or around October 19th, 1976. I'm adorable. That's a picture of baby Mr. Janowski. So this is a picture of baby universe. So if you've ever seen a picture of, I'm sure you have, a picture of the Earth where they smear the whole thing out into a oval like this so that you can see the whole thing at once, that's what's going on here. So this is an image of the entire sky. This was taken from WMAP, I think, Wilkerson Microwave Anisotropy Probe or something. A high resolution space satellite took this, and this is an image of the whole sky, and this is an image of the cosmic microwave background. So when you're looking at this, areas that are red are a little bit warmer than areas that are yellow, which are warmer than green, which are warmer than light blue, which are warmer than dark blue. So the blue areas are the coldest, and the red ones are the hottest. Now, it may seem when you're looking at this like some places are very hot and some places are very cold. In fact, they are all very cold. And the difference between the absolute hottest and the absolute coldest parts here are, I don't know if they're thousandths of a degree Kelvin. It's the tiniest little difference between the hottest and the coldest parts of the cosmic microwave background, which leads to a couple of very interesting cosmological questions. One question is, why is it so very close to being uniform all the way across? Why is the temperature almost exactly the same in every single direction? And the other question is kind of the flip of that question. Well, why is it almost but not quite exactly the same? So big picture stuff, basically where it's a little bit hotter, those little red specks, you tend to have a little bit more stuff. So that's where the first stars and the first galaxies would form. So this picture contains a lot of insight into the large-scale structure of the universe and the entire history of the universe up until the present day. So big stuff. So again, this picture, 500,000 years, it should say 380,000 years. This is the recombination. So at this point, maybe you can tell going this way that universe very, very hot and dense, and then all of a sudden it has become cool enough that the universe is now transparent and light can travel. So this light we're seeing here in this image is the light that was traveling from here, from just 500,000 years, from 380,000 years after the Big Bang, which at that point was very, very hot. But because the universe has kept expanding and expanding and expanding ever since then, that light has gotten stretched out and redshifted and cooled down, basically. So instead of being tens or hundreds of thousands of degrees Kelvin, it's only about 2.7 degrees Kelvin. So here is your timeline of everything. Little things to point out too. You'll notice that this thing starts out very narrow, and then all of a sudden, real quickly, it shoots out a lot, and then it stops shooting out as quickly. It's still expanding, but not as quickly. This is called inflation. This is, I forget when they first came up with this idea, maybe the 80s. Alan Guth was the guy's name, but whatever. This video is getting too long. Anyhow, if you find this stuff interesting, watch this video too. I will put a link in the description. So, moving on. There are 4 fundamental forces in the universe. So also the astronomy students, you would have heard of this. The 4 fundamental forces in the universe are what's called the strong nuclear force. This is the force that holds the quarks together inside the protons and the neutrons, and it holds the protons and the neutrons together in the nucleus of atoms. That's the strong nuclear force, far and away the strongest force. We also have what's called the weak nuclear force. So the weak nuclear force, it's not as strong as the strong nuclear force. The weak nuclear force basically turns protons into neutrons sometimes, and sometimes it turns neutrons into protons. So it seems kind of weird, but this is the thing that makes the sun work. The next force you have is the electromagnetic force. So yes, everything that's electric or magnetic, all of those things, but also electromagnetism is what holds the electrons to the nuclei. So all of chemistry is electromagnetic, and everything that's made of chemicals is electromagnetic. So this is a force you deal with every day. In fact, all of the forces we've dealt with all year long, with one exception, are the electromagnetic force. So if you push on something, if you again, we're doing social distancing, but if you've got a neighbor, if you were to push on your neighbor, you might think that you're touching your neighbor. In fact, you're not really touching your neighbor. What's happening is the electrons on the end of your fingers are getting close to the electrons in that person's arm or shoulder or wherever you're shoving them. And your electrons and their electrons have the same charge, and like charges repel. So when you think you're actually touching somebody, what's really happening is your electrons are getting close to theirs, and the electrons are pushing each other off, but nothing actually ever touches. So yeah, why not throw one more big idea into the mix? Nothing actually ever touches, which is weird. And there's more to it than that. That's only thinking of it classically. Quantumly, it gets even weirder. But I digress. So yeah, the normal force, tension, any kind of elastic force in a spring, all of those forces, friction, all of those are electromagnetic forces. And then there's one force we deal with every day that is not the electromagnetic force, and that force is gravity. So gravity is going to be the topic of this chapter. So on this chart here, we have the 4 fundamental forces. So every force, we think there are only 4 fundamental forces in the universe. There's some kind of fringe group right now who claims they found a 5th, but nobody really believes them. So here we are in April 2020, and I'm going with that there's just 4 fundamental forces. Maybe I'll have to update that in a couple of years, but for now there's 4. So anyhow, what we're looking at on this table, here are the 4 forces. Here are the strengths of the 4 forces as compared to the strong nuclear force. So the strong nuclear force is 1 times as strong as the strong nuclear force. That makes sense. And this column tells you the range of the forces. So the strong nuclear force is far and away the strongest force that there is. However, it has a really tiny range. So this is 1 over, it's 10 to the minus 15 meters. So that's 1 over 10 to the 15 meters. So what does that mean? That means 1/100th of a millionth of a meter is the range of this force. So within that range, the strong nuclear force is the strongest. If you go outside that range, the strong nuclear force falls away to basically nothing. So that's the strong force. The weak force, this is the one that turns protons into neutrons and vice versa. It is way less strong than the strong force. This one is only 1 over 10 millionth of a millionth as strong as the strong force, and it has an even shorter range. Now you get to the electromagnetic force. So the electromagnetic force is about 1 over 10 squared. So it's about 1/100th as strong as the strong force. And its range is infinite. So if you take 2 charges, put them anywhere in the universe, they will exert a force on each other. It gets to be fairly weak as they get far away, but yeah, they will always have a force. The range of the electromagnetic force is infinite. And then you get to gravity. So gravity is 1 over 100 millions of a millionth, 1 over 100th of a millionth 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 has the strong force. So this is far and away the weakest force. And it's only this fraction as strong has the electromagnetic force. And its range is also infinite. So even though gravity is far and away the weakest force, and it's only that fraction as strong as even the electromagnetic force, gravity is still very important. Gravity builds planets and stars and solar systems and galaxies and clusters of galaxies and groups of clusters of galaxies. So all of the big things in the universe end up being built by gravity, even though gravity is the weakest of all the forces. So why is this? Well, one thing is gravity has an infinite range. Gravity always acts, any two masses anywhere in the universe, they're always going to pull on each other. So infinite range, that's good. However, the electromagnetic force also has an infinite range. And the electromagnetic force is many, many times stronger. So why doesn't the electromagnetic force build all the big things? The other reason is that gravity is always attractive. So like charges repel, opposite charges attract. And what that means is the electromagnetic force tends to cancel out over big distances because you'll have some positive charges and some negative charges. And some of them are pulling on each other and some of them are pushing on each other. So that tends to cancel out. Whereas gravity is always a pull. Gravity is always attractive. So finally, we get to the title slide. Chapter 13, Universal Gravitation. You'll notice we went from Chapter 10, Rotational Motion, to Chapter 13. Chapter 11 would have been torque, but we always skip that. And Chapter 12 would have been angular momentum, and we never have time for that one either. So we've got to do gravity. So we do gravity. Oh, and my computer better not freeze. But we're not actually going to start much with gravity because we're already at the review slides, and I'm sure this video is getting really long. So, how long ago was the Big Bang? Do you remember the number? 13.8 billion years ago. So here's your timeline of everything, and the universe is 13.8 billion years old, which is a ridiculous claim. It's an extraordinary claim, and extraordinary claims require extraordinary evidence. So what are our two main pieces of evidence for the Big Bang? Well, the first one is that the universe is always expanding. And the second one is that we have the cosmic microwave background. So we've known this one, the universe is expanding, since about the 1930s. It could have been the 20s, actually. I forget when Hubble figured out his stuff, but around the 20s or 30s. And that was strong evidence for the Big Bang, but not everyone really believed it at that point. And then 1964, Penzias and Wilson accidentally discovered the cosmic microwave background, confirming the Princeton guys. And I meant to mention one thing. I said the Princeton guys, Penzias and Wilson won the Nobel Prize for this, and the Princeton guys got shut out. And that was true up until last year. One of the Princeton guys did win the Nobel Prize for physics last year. So I don't actually know if that last year, I think it was actually early 2020 is when that happened. So he did finally win. One of those guys, some of them had died by this point, of course. But one of them did kind of win the Nobel Prize kind of for his lifetime contributions to cosmology, the study of the universe on the largest scale. Good stuff. And again, what are the four fundamental forces of the universe? The first two kind of come in a pair. You have the strong nuclear force and the weak nuclear force. So the strong force is the strongest. The weak nuclear force is actually the third strongest. The second strongest of the four forces is the electromagnetic force. And the weakest of the four forces by far, and yet the force that builds all of the big things in the universe, and the force that is the main subject of this chapter, is gravity. So here again are the forces, here are their strengths, and here are their ranges. So I don't have the clock running. I don't know exactly how long this video is. I'm sure it's gotten to be very long, longer than I would have intended. But hopefully you found this interesting. And if you really should, I'll put the links in the description to those videos. Watch all of those videos. Wonderful, fascinating stuff. This is the big stuff. This is, all of this stuff is reasons to really love physics. So hopefully you're finding this interesting.